In the past 10 years, I think the question about the intelligence or artificial intelligence has captured people's imagination. I'm one of them, but it took me about 10 years to try to really understand, can we actually make understanding intelligence a truly scientific or mathematical problem to formalize it? You probably will get some of my opinion and also the facts about it. And probably will change your view what is intelligence is, which is also a very soul-searching process for me. How do we clarify some misunderstandings, the common misunderstandings about the intelligence? Through this journey, maybe we'll gain an entirely new view about what we really have done, right? In the past 10 years, the practice of artificial intelligence, the mechanism we have implemented, all the mechanisms behind all the large models, deep networks, and the large models are, and the true natures, and hence understand their limitations, and also what it takes to truly build a system that has intelligent behaviors or capabilities. I think we have reached the point, right? We'll be able to address what's next for understanding even more advanced form of intelligence. What's the difference between compression and abstraction? Difference between memorization and understanding? I think for future, those are the big open problems for all of us to study.
MLST is supported by Cyberfund. Link in the description.
The idea of having to traffic in squishy people in order to make our systems go is not immediately appealing, let's put it that way.
This episode is sponsored by Prolific.
Let's get few quality examples in. Let's get the right humans in to get the right quality of human feedback in. So we're trying to make human data or human feedback. We treat it as an infrastructure problem. We try to make it accessible. We make it cheaper. We effectively democratize access to this data.
Professor Ma, it's amazing to have you on MLST. Welcome.
Thank you for having me.
So normally I ask guests to introduce themselves, but given your stature in the field, I think it's best that I give you an introduction. So Yi Ma is a world-leading expert in deep learning and artificial intelligence. He's the inaugural director of the School of Computing and Data Science at Hong Kong University and director of the Institute of Data Science at the University of Hong Kong. He's also a visiting professor at UC Berkeley, where he previously served as a full professor in electrical engineering and computer science. He's an IEEE Fellow, ACM Fellow, and CM Fellow, whose pioneering work on sparse representation and low-rank structures has fundamentally shaped modern computer vision and machine learning. His recently published book, Learning Deep Representations of Data Distributions, proposes a mathematical theory of intelligence built on two principles, parsimony and self-consistency. This framework has led to white box transformers, known as crate architectures, where every component can be derived from first principles rather than empirical guesswork. So, Professor Ma, tell me about your book.
About 8 or 7 years ago, deep networks, deep learning has been pretty, changed the practice of machine learning or artificial intelligence in the past decade. About 8 years ago, I had a chance to get back to Berkeley and gave me a chance to look into these topics more deeply, try to understand it from a more principled approach. And hence, the book is kind of summarizing the kind of progress we made in the past, 8 or beyond years, myself, my group, as well as many colleagues, trying to understand the principles behind the deep networks, explain it from our first principle. And in that journey, we also seems to embark on a little bit beyond that. Find something probably more general behind that is the intelligence at a certain level of intelligence. Hence, when I get back to join Hong Kong U about 2 years ago, had a chance to design or redesign some of the curriculum to reflect those some of the progress updates in our field, the rapid progress in our field. So my students and colleagues decided that maybe it's time to systematically organize this body of knowledge and reflect it as a textbook. as well as a new course, which I'm teaching this semester. Likely will be offered as well at Berkeley next semester. So this is actually a first time probably we try to provide a more principled approach to explain the deep networks, as well as some principle of intelligence.
And these principles are parsimony and self-consistency. So it's an ambitious idea that these principles could explain natural and artificial intelligence. What do you mean by that?
Intelligence, artificial or natural, or whatever adjectives you add to intelligence, we have to be very specific. It's a very loaded world, right? I mean, even intelligence itself may have different levels, different stages, right? So it's high time we clarify that concept scientifically and mathematically, right? So that we'll be able to talk about, study intelligence, the mechanism behind it at each level. There's a more unified principle behind even different stages of intelligence. There's something in common. There are also things are different. So it's high time we do that. One of the intelligence at the level is that common to animals and human, right? Human, we're animals. That level of intelligence is what we think are very common to all life, which is how memory, how we learn knowledge about the external world, and then memorize as part of our memory, and use that to predict, to react to the world, help us make decisions, predict and make better decisions for survival, and so on and so forth. That's very, very common. And this is the level of intelligence we're talking about, very much for the book as well. Right, and hence for this level of intelligence, how our memory works. Today we also have a fancy word for memory. We call it a world model, right? And it's how we develop such a memory, such a world model, and how the model gets evolved, and how we use it. That's actually, this is the level of we talk. So we actually believe that for this level of intelligence, for how our memory formed and how they work, is precisely the two principles are incredibly important. And we believe they are necessary. Is that memory or knowledge is precisely trying to discover what's predictable about the world. Hence, for all understand, all such information have intrinsically very low degree of freedom. We call it low dimensional structures. And hence, the way to pursue such knowledge is precisely through trying to find the most simple representation of the data. And hence, compression, denoising, dimension reduction is actually all just different words to pursue such knowledge, such a structure. And hence, that's the word captured by the word parsimony. Finding, making things as simple as possible, but not any simpler, right? So this is Einstein says this word, this sentence Einstein used to describe science. Actually, that's also what the intelligence, at least at this level, is precisely doing the same thing. The second part of the sentence, not any simpler, precisely says consistency. Make sure your memory is actually consistent with, be able to simulate the world just right. Not any similar. If you're simpler, you may lose part of the predictivity, and also ability to predict it well. And so that's actually those two actually coexist, we believe. At least those are the two principles, parsimony and the consistency or self-consistency, are actually the two characteristics about how our memory works.
So we want to have understanding which carves the world up by the joints, which represents the important invariances in the world. And the thesis is, I think, that compression might be necessary for understanding. My possible concern with that is that what we are doing with machine learning is representing extant examples of a long phylogenetic tree of evolution. Mm-hmm. So to what extent does knowing their representation now help us? Do we also need to know how they evolved and where they might go in the future?
The process to acquire knowledge, to gain information about our outside world, That's a compression. Find what is compressible, what has orders, what phenomena has orders, has low-dimensional structures that allow us to predict, to rule out variabilities, to predict world tomorrows or predict world better in that sense. So in the sense that that is the ability we believe is really what intelligence is all about. At least the common intelligence we're talking about, right? We can talk about the more higher level intelligence later. And if you look at the history of life, how life was developed, so we actually come to believe, right? The mechanism that laws that governs the physical world, we call it physics, right? But what is the mechanism that governs the evolution of life? I think it's intelligence, right? Even the process you mentioned that through evolution and life evolves. Precisely, they learn more and more knowledge about the world, and they encode them through DNAs to pass it on to next generation. And that is a compressing. That's a process to compress knowledge that learned about the world through our DNAs. But the mechanism to update it is actually very brutal force, and through random mutation and the natural selection. Yes, it does evolve, it does advance, but at a huge cost of resource, time, and also very unpredictable. Which, if you're acute, you probably observe there's some similarity with how current big model evolves, right? Many groups try without principle, try and error, empirical, and the lucky ones survive and gets advocated, everywhere and become very, very popular, right? Dominate the practice. So in a sense that you can make the analogy, right? I think to the people, students ask me at which stage our artificial intelligence is at today. Then there's already a allergy in nature, right? We are very much at the early stage of the life form, right? And so hence that is a compression process. That's a process that also gain knowledge about the world. But of course, later on, we develop individual animals to develop the brain, develop neural systems, develop senses, including visual and touch and so on. So we actually you start to use a very, very different mechanism to learn, to compress our observations, to learn knowledge, and to build memories of outside world. And even individuals start to have that ability rather than just inherit knowledge from their DNAs. So that's a different stages and then that part of the knowledge is no longer encoded in our genetics, in our genes, but also in our brains. And that's actually a level of intelligence we talk about most of the time these days. Which is common to animals, which is common to humans, and the knowledge, or the intelligence we talk about, what brain functions.
Yeah, I mean, I think we would definitely agree with the statement that intelligence as a system produces artifacts. So Chollet's example is a road building network. It produces roads, and the system has adaptivity because it can create new routes where they weren't there before. And then there's the question of, well, there are many ways to compress a thing. So some ways of compression represent the world at a deep abstract level and some don't. So we might argue that LLMs today, even though they do compress the data, they only compress it in a superficially semantic way. And then there's this notion of, well, maybe we agree that intelligence is about the synthesis of new knowledge. So it's the acquisition of new knowledge. But we can only do that if the knowledge we already have represents the world at a deep abstract level. So rather than it being random mutations in evolution, it's very, very structured because the processes are physically instantiated, which means rather than just doing something completely random, it's guided by the process which created. The manifold hypothesis comes to mind, which is this idea that all natural data falls on some low dimensional, structure, with a low intrinsic dimension. And the other thing that springs to mind is, I mean, I'm a fan of geometric deep learning, which is this idea of, we should imbue inductive priors in the system which represent symmetries and geometric structures in the world. And I think as a principle, that's deeply embedded in this idea.
Exactly. If you look at my whole life, I have written 4 books, right? My early interest is studying computer vision, and the first book is about 3D vision. And from that work, I studied multi-view geometry. From that work, in my whole book, all the 4 books is actually about one theme. I realized that it's about structure in the data, especially all reflected in the first book of 3D vision. The last chapter, I realized precisely about what importance of symmetry plays in our perception, right? And we perceive an object, we naturally has a, so human being, remember our vision, we already realized a long time ago, right? These days people always about the vision is about recreate 3D. Absolutely not, right? All the people says we just multiple images recreate the whole point clouds, mesh, scientist function, NeRF, Gaussian splatter, right? We recreate the scene. See, I can see from multiple angles. Is this 3D understanding? Or we create some videos like Sora, look at it, looks good for, absolutely not, right? This is not the representation or understanding of a world model, right? Our understanding is far beyond getting a whole bunch of, point clouds or Gaussian splatter we can view from different angles, right? Have you noticed that when we see something in 3D, we get excited because we understand the 3D. We understand the content. We parse it already in our brain. But the machine has no idea what the heck is in there, okay? It's just a bunch of point clouds. It's a depth map, okay? When we see this change in angle, we saw 3D. We already automatically recognize, this is a hand, this is a body, this is a cup, this is an apple, right? We do that. We fill in that information with our brain. We think machine, once they can recreate the 3D, they ought to understand that. This is completely wrong, okay? Many work, they say we are building 3D model by creating something for people to look at. That's completely not the purpose. So look at our vision model, right? We have hippocampus, we have our IT cortex, highly structured. We understand the relationships between our view-centric, object-centric, and allocentric representation, right? Neuroscientists understand this very well, right? Scientists understand this very well, but not computer scientists, right? Not the computer vision scientists. Some do. See, for example, I give you an example, right? In order to do spatial, we actually did a test with Jan Kuhn about a year ago, tested all the top multi-model models, huge models, GPT, that Gemini, right? To do very simple test. The title of the work called Eyes Wide Shut, right? And it's a very simple test. Just test the given images for those language model or a big model, multi-model, highly trained, highly commercialized models that do they understand the reasoning, spatial reasoning? What is on the left of something? Or how many objects there is in the space? Right? What is behind something? What's on top of something? Very simple spatial. The question requires a little bit, not even very deep, spatial understanding. But all the models fails miserably. And the majority of them actually even worse than random guess, right? I think only Gemini and GPT is a little bit above human, a little bit about the random guess, okay? Far below human understanding. So that's the status, right? If I see do those, meaning that those actually 3D understanding is very, very difficult. But human, we do this effortlessly, right? So I can easily point to you, right? Please hand me the bottle to your left. If you want to find, let's say, a shopping center, right? Say, go through the door, turn right, go to the, once you get outside of the building, head south, right? So through this, remember, just through this simple sentence, already we switch from view-centric to object-centric to allocentric, right? So our brain, if we don't have this kind of model, this kind of highly structured 3D models, forget about, people talk about embodied AI or world model, right? We cannot conduct this very simple spatial references. Interacting, we have the world model is not to visualize, We build a 3D model to interact, to manipulate, to influence, right? We're not building a 3D model just to, oh, this looks like I can change my view, look at it from this view, that view, right? Just visualize. No, turn 360 degree to visualize. No, we don't do that. That's not our purpose, okay? Unfortunately, but there's, it gets distracted for that kind of visualization. It looks cool, but almost to us, if you really work on robotics for all kinds, navigation, locomotion, manipulation, they're actually pretty. The usage is pretty limited. I won't necessarily say they're useless, but they are actually pretty limited. Yeah.
We should introduce the coding rate formula. I did have a question about that, which is there's an epsilon on there. So there's a bit of a question of how do we tune that and what does that mean? We should also we've been talking about this a little bit, this concept of an LDR, so a linear discriminative representation. And just more broadly, with these inductive priors, there's always the question of when we do abstraction to model regularities in the universe, there's always a little bit left over, isn't there? So to what extent can we think of these things as natural?
Actually, you touched upon about the epsilon. You touched upon a very, very deep question. It actually took me almost 30 years to understand it, to be honest, right? We did mention that early on when we try to differentiate measure different volumes. It turns out lossy coding is necessary. It's not just something that is something hacky. It actually turns out to be necessary and to do lossy coding. In fact, recently we start to realize that noise actually plays very different roles. And yet it's very confounded, very confusing to many people. Even this is something actually my students will certainly realize. We actually probably will have some papers about it. I can elucidate this a little bit. If you think about the whole diffusion denoising model, right? People are very popular right now to do. Why do we add noise to data, right? And to the whole world? Because we don't know where the distribution is, right? So there is a phrase everybody knows, all roads to Rome, right? So why is that? Has anyone given a thought to why all roads to Rome? Because, very simple, at some point in history, Rome builds the road to reach the whole world, right? That's a diffusion process. Then if you want to know Rome, then you do the denoise. You follow the same way back. You get to where the Rome is. So that's the no-dimensional structure. That's where the knowledge is, right? That's the oasis is, right? So hence, it's a very natural process that we add noise. Is adding noise to the data distribution is precisely we building the roads. And the denoising brings us back. Remember where we come from, and so on. And that's a big epsilon. We have to add noise to reach the whole Earth. There's another noise, right? Remember, we only have isolated sample. Even we talk about manifolds, right? But how many points you have on the manifolds? How many points you observe them? They're always finite, right? But why do you call it a continuum? Why do you collect dots as lines, planes, surfaces? When do you do that? Hence, noise plays another role. Within the manifold, even you have finite samples, if you allow lossy coding, if you allow packing spheres in that, things start to connect. You start to connect. Noise is very important to help to connect the dots, right? We all know the phenomena of percolation, right? We see raindrops on the floor. You only see two phases, right? One phase is all the dots are isolated. Another phase is all things gets wet. You never see anything in the middle because there's a sharp phase transition. Once the sphere, once the dots, the density gets high enough, it collects everything, right? Maybe that's a phase transition we realizing a connected plane is a better solution to explain all the data, more parsimonious, more economic. The cost to memorize all the dots versus memorizing as a plane start to switch. Maybe abstraction has something to do with that. I don't know. But from a compression point of view, this can already allow us to explain when do we go from zero-dimension samples to prefer a low-dimensional manifolds. And also how go from that low-dimensional manifold to reach the rest of the world, right? So you can see even in this process, noise is already playing, the epsilon plays different roles. And at some point, they gets collected, right, around the surface. That's we still try to figure out what happens. But at this big two phases, we already know, right? The role of epsilon actually plays different roles, right? And I think definitely in the past many years, our understanding about the subject, how do we compress, how do we pursue the low-dimensional structure from finite samples, our understanding about this problem has truly advanced dramatically. I'm very happy. Honestly, this is a question baffles me when I was a graduate student. You can see even my early work about the lossy coding, lossy compression reflected my baffledness about it. And I'm really feel very thrilled that I recently start to understand those things in a more unified, more not only in theoretical way, but also even an algorithmic way.
Yeah, it's so fascinating that we can look out the window and we ignore so much detail. We don't look at the leaves on the roads. We just find that structure. And that's why when I watched your presentation, I was very intrigued when you said that denoising, iterative denoising is a form of compression. Yep. I wanted to mention your ICML 2024. So last year, it was in Vienna, right, with Wang. And you found that when you have loss surfaces using this technique, they are dramatically different. They're very smooth. There's no kind of harsh local minima and so on. What's the intuition for that?
In fact, the phenomena, our understanding about those phenomena is actually going back when early days we studied sparsity. When your data lies on very low dimensional sparse surfaces, planes, right? Low dimensional planes, orthogonal planes, or low rank matrix, right? And in there, we learned a very big lesson. The object function to evaluate those sparsity or low dimensionality, those functions are highly nonlinear, non-convex. But yet, traditionally in all our orthodox understanding about the non-convex optimization is they're always hard, right? And in the general class is NP hard, and there's lots of local spurious local minima. You get stuck with local minima. There's some stagnant critical points, flat surface. So basically, the worst picture is very worse, right? It's a nightmare. But through the study of those low-dimensional structure, sparse structure, that's what's actually featured in my previous book, right? Low-dimensional structure of high-dimensional data analysis. We actually realized that if a lot of non-convex problem, even the optimization problem had non-convex landscape, if those problems or even those measures arise from nature, very natural resource, those structure actually are very highly regular, has symmetry. The landscape actually are extremely benign, right? Quite contrary to our common understanding about nonlinear optimization at all, right? This is a complete 180-degree flip of views. In fact, even the higher dimension helps. The higher the dimension, the better. We call it the blessing of dimensionality. So those regularity, those symmetry will tell us the landscape of this object function are actually beautiful, right? And first of all, they're highly regular. There's no stagnant, there's no flat surface. There's no too many spurious local minima. And even the local minima, they already have very clear geometric or statistical meaning. And hence, those landscapes are very amenable for very simple algorithm to find the optimal solution, such as a gradient descent, which almost indirectly explain why even we're doing even modern training neural networks and many more, we're searching low dimensional distribution in very high dimensional spaces. But somehow gradient descent always end up with somewhere nice. Okay, yeah, fine. You can run a long time, but somehow you always end up with those landscapes are not that hard to traverse, right? So it actually precisely because those object functions are highly regular. Hence, now get back to the rate reduction object function, right? If you look at the object function, it's not something arbitrary, right? It's counting the volume of the whole minus the parts, right? It's something extremely objective, right? It's not like a loss function people come up with randomly, or add this term, weighted sum at different weights. If you use this, sort of an empirical penalty or empirical, or even some kind of ad hoc. So all the terms are describing physical volumes of the data, right? Hence, you should expect those are the quantity arise in nature. Then from our lesson, we realize indeed, those object function has very benign landscapes. Even the local minima, not only the global minima, corresponding solutions that are give you orthogonal subspaces, even the local ones, right? They are not the global optimal ones. They have similar geometric structures, right? And there's no other weird critical points that will slow down the search for those minimas. So that's actually quite interesting. So you can see this revelation allow us to understand, right? Where maybe intelligence is precisely exploit and harnessing those things. So there's actually a misunderstanding about last 10 years. When we understand intelligence more and more, there is a very big misunderstanding about intelligence, right? In machine, you study maybe machine learning theory, right? We have a tendency to believe intelligence, especially intelligence at nature, is designed to solve the hardest problem, the worst case. I actually beg to differ. Intelligence is precisely the ability to identify what is easy to address first, what is easy to learn, what is natural to learn first. Then only when that has been done and the resource permit, we start to get into more and more advanced tasks. Not everybody needs to learn advanced mathematics to survive. Animals don't, right? Nature find what is the easiest things with minimal energy, minimal effort almost to learn the most knowledge so they survive the best, right? Again, this is the principle of parsimony at play. There's another level of resource parsimony at play here, right? Hence, once you realize this, you realize in understanding intelligence should be really understand what's really most common, right? The low dimensional structure, most easy ones, smooth ones, benign distribution, easy to get away with fewer samples, right? And very easy to formulate. In fact, that's how science progresses. A lot of the physical models, Newton's law, they're very simple. They discover the simple ones. Then we gradually reach to general relativity and then to quantum mechanics. Those equation gets more and more complicated later, right? So this is hence the same process. We identify what is the most common first, right? What is the most easiest task first? Hence, we don't want to, many of the machine learning theory tends to derive a bounds for the worst cases. I think we probably should think twice, right?
I love that characterization. It's similar to the least action principle in physics.
Exactly.
In a sense, we solve problems by taking many, many steps in different directions. I think we still leave a little bit of entropy open. We don't do pure hill climbing, but collectively we acquire these stepping stones, and the totality of that process is we solve very complex problems. But I wanted to touch on, you raised a very interesting point, which is we notice that when we have very large deep learning models, they tend to almost self-regularize, and they learn better. And there's this phenomenon of double descent and all of this. Tell me about that.
Fascinating question. Actually, this question actually needs to really bring me back to early days when I tried to understand deep learning. When deep learning arises, there's a lot of phenomena we try to understand. I'm one of those, right? Try to understand those phenomena. There's some good about dropout, something about thresholding, different thresholding. There's something about normalization. Then we also come to somehow the model are very big. And the parameters a lot. Somehow the deep networks do not have the tendency to overfit. Somehow they still generalize okay, right? And then of course people realize that there's a sort of rather unlike the traditional classical bias variance bias trade-off, but there's time to the double descent. I actually wrote a couple papers about it and about the normalization, about everything. Around 2000 or late 2019, I really told my students we should stop, not to explain those isolated phenomena. We only see, we're like the blind man to elephants. Each one say a little piece, each theory try to explain a little bit. I think there should be a total explanation to this if we get the big picture. All these are just the consequences or implications of that. suddenly, at that time, we start to touch upon the concept of maybe that the process of deep network are optimizing something. The layer-wise is realizing optimization. They are optimizing objective that promoting parsimony, promoting no dimensionality. Once we realized, actually, I was quite thrilled. So then I told my student, from now on, we will no longer write any papers about overfitting. Why? Because if the neural networks the operators try to compress, try to realize certain contracting map, compress volume, then you will never overfit, right? Even I overparameterize, you will never overfit. A simple example, if I have data lies on a straight line, a one-dimensional curve, whatever, I can embed this one-dimensional line in a 2-dimension, 3-dimension, or a million dimension. But if my operator is always layer-wise, each iteration, my operator is always just shrinking my solution towards the line, right, in all directions, I would never overfit. Even I overparameterize, embedded the line into a billions of dimension. I have a billions of parameter, but collectively, all those billions of parameter are all shrinking my solution, pushing the solution, denoise it, compress it towards the line, right? Like a power iteration, just like a PCA, right? Power iteration is in regardless of what the dimension embedded, computing the first singular values, right? It's always powerful, or it's converged with the same speed. You never over. So compression, by nature, if the operator are performing compression or denoising, which means this process will no longer overfit anything, right? If you conduct it right, if you converge, the solution will converge on the structure you desire for.
That raises a natural question. We were interviewing Andrew Wilson from NYU, and he's got this, several papers about implicit biases, where you kind of have a combination of, hard biases with symmetries and everything in between. And if what you're saying is true, then why do we need inductive biases at all? Could we not pare back a little bit and just have really big models?
No, I see. So this is the thing, right? Exactly. So this is the thing. I was, early on, people don't understand deep networks, and there's a lot of empirical trial and error. People tends to use the phrase inductive bias to either as some kind of magical sauce that either explain the failures or success of you do certain way to the neural networks design, or how do you train the neural networks. To be honest, for a long time, I never understand what the inductive bias is. And maybe some regularization, some people explain some structures about network, about the data. But nowadays, in my recent work, I said probably, at least from what I understand, all the inductive bias should be formulated as first principle, right? At least we were able to, for example, deduce all the deep network architectures, including the recent white box crate or transformer-like or ReduNet-like, ResNet-like architecture, or mixture of expert-like architecture, all from the only inductive bias is that assuming your data distribution you are pursuing are low dimensional. Okay, you can already get the form, the main architecture or form of operator for each layer as a res structure, mixture of expert structure, and those operator per layer are precisely conducting denoising, compression, or contrasting. Are there additional assumptions you can make? Yes, you can. For example, if my job is not just to compress the data as it is, I also wanted to for example, in object recognition, I also want to make all data, I want my classification to be translational environment, which is symmetry, right? If you allow my task will be environed to certain group action, I want to compress them together. Voila, what do you get? Then you still compression, then you get a convolution, naturally, as the structure for the compression operator. So convolution is not what we impose upon, it actually results from the first principle, the quote-unquote inductive bias you assume. You want to compress your data. Also, you want your compression to respect translation environment or rotation environments. That's the result. That is the characteristic of the compression operator for you to achieve that task, right? So there's a lot of so we don't want to build in the inductive bias while we're searching for the solution. The inductive bias, in my understanding, should be the very assumption we make in the very beginning. The rest should be deduction. The rest should have no induction anymore. Otherwise, we're doing trial and error, right? The inductive, so basically when we build a theory, we should have done all the inductive observations, experiment, and assumptions already. The good theory should start with the very few inductive bias or assumptions or axioms. Then the rest should be deductive. I call that first principle.
We've been speaking about parsimony, which is what to learn, and self-consistency is about how to learn. And we can sketch out a journey, I suppose, from control theory to learning. And also this methodology has some interesting results, I think, around the continual learning problem. So let's sketch that out.
You can see, right? So the compression or the even the rate reduction to try to pursue the data distribution and also transform it, and that's the one way direction. There's no theoretical guarantee either your data is sufficient to identify that. You may start with very, very few samples. There's no way the data is sufficient. I mean, maybe the apple, there are 5 types. Maybe I only say 4 types, right? So, but that process goes on. You do compress what you have and reach a memory, right? And there's no guarantee, even during that process, you may not get stuck. Maybe there's not enough iterations. So memory you get may not be accurate, may not be correct. Hence, how do we check? How do I further develop, evolve, improve my memory? Or make sure my memory actually be able to authentically predict. This is a word model. The model is accurate, right? So you actually have to decode it. You can think about the memory formation is an encoding process. Then from a memory, I want to decode. I want to predict what's going to happen next second from what I observe right now. Or at night, I may want to dream what I have, right? So that's actually the decoding is actually allows us to check if my memory serves to be right, how accurate I can predict next step. So hence, this actually already form a sort of auto-encoding framework. Now, of course, auto-encoding, if I have access to both the observation and my memory, just like training our big data models, I have control on both ends. I can just force auto-encoding back end to end, right? The people like to talk about it. But in our natural, in a natural setting, in the animal or human setting, we don't have control on both ends, right? We only have probably control of our own brain, what's inside our brain, right? We never really quite have access to measure if my prediction of the 3D world. For example, right, the frame of the picture is rectangular. Do I ever measure it? Right? You don't have to measure it, but somehow everybody believes, the model is correct. How do we do that? Right? Hence, there's actually a self-correcting process. In fact, this is actually probably the idea actually goes back to Norbert Wiener, right? And how animal be able to correct its error without, cats can capture something very accurately. Or even make one single mistake, they can correct that very accurately, right? So somehow they're be able to build a world model very consistent, self-consistent with the world without actually physically measure their errors, right? So hence, this is the idea about you actually loop it back to your brain and close the loop, right? And allows you to constantly predict, and based on your prediction and your observations, check if there is a difference between your prediction and your observation within your brain, where if there's error, and using that error to correct. Turns out, this is a work with my student. Turns out you cannot do this. Of course, our observation will lose information, right? We'll introduce noise or lose dimension or lose information. But turns out, as long as the distribution of the world, the data, the distribution of the world is low dimensional enough, even your encoding process, your perception process is noisy, this is still doable if precisely when the distribution of the data outside world has enough structure, it's highly low dimensional. And hence, your brain has enough degree of freedom to discern any differences. So this is actually quite interesting revelation for us to realize that the low dimensionality is not just some or technical assumption. It's actually necessary for this kind of closed loop learning to be possible. And once you be able to close loop, then you actually constantly observe, constantly predict. Hence, you can constantly use your memory to predict and correct it. Hence, support continuous learning, even lifelong learning, right? Our memory, Rome is not built in one day. Our memory is never built in one day. We constantly improve it, constantly revise it. And this is the mechanism of intelligence. Hence, this mechanism itself is already generalizable. Hence, you don't need to add the adjective general in front of intelligence. There's no point of calling general intelligence. If you implement the intelligence mechanism correctly, it's already generalizable. The knowledge learned by this mechanism at any point of time may not be generalizable. The mechanism does. Right? This is a very big confusion. We think if I accumulate enough knowledge, it's generalizable. No, it's not. Will never be. Any scientific theory, by definition, being scientific is falsifiable, which means it's limited, right? Can only explain the world up to a certain point or certain accuracy. There's always room for improvement. The scientific activity, our ability to revise our memory, to acquire new memory, that is a generalizable ability. That is intelligence, right? Through natural selection, early days, through our feedback control, feedback correction, through the human history of trial and error, accumulating empirical knowledge, through scientific discovery, is all doing this, right? That is common behind intelligence, right? Not the memory accumulated up to a certain point. So even we manage to memorize the whole world, the knowledge we have in the whole world, we will no longer be able to apply when we find ourselves in a new environment, in a new situation, observe some phenomena we have never seen before, right? Hence, that's the limitation of, you try to gain general intelligence through just accumulating enough knowledge. Right.
We should talk about your CRATE series of architecture. So CRATE stands for Coding Rate Reduction Transformer. And you made some very interesting discoveries. So for example, multi-head self-attention can be derived as a gradient step on rate coding, and also MLPs as sparsification operators. And also you were talking about how something like a transformer could be described in a principled way. So there's this interesting thing, isn't there, that we designed we didn't even design them. We kind of empirically tried with lots of different things, and we happened upon the transformer. But something like that can actually come about from a first principles approach.
If you look at the past decade or so, evolution of also it's kind of natural selection process for the big models, right? From early days, AlexNet, LeNet, AlexNet, VGG, or then ResNet or transformers. By the way, this is just one of those for survivors, right? As I said, just like natural selections, right? Remember, people don't forget. There's a time, there's a very popular areas called AutoML, right? People tend to do random search for better architectures, right? Somehow, why only a few survived? There must be a reason, right? They must capture certain structures. They must did something right. Now, from our understanding so far, the ResNet actually capturing the fact that each layer should be doing optimization. The ResNet precisely reflect the iterative optimization architecture, right? And the MOE precisely capture fact we're trying to cluster, compress what's similar, and discern or classify what's different, or contrast what's dissimilar, right? And you wanted to develop different experts, right? We call them experts. We call them a cluster. We call them a group. So be it, right? And the transformer, again, right, is capture what is the correlation. The self-attention head is precisely compute what is the correlation in the data, covariance in the data, what's correlated, and using that to further sparsify, further classify things, to organize the distributions. They must do something. They somehow close to something right? So also it's almost like a belief for us, right? If we believe there's something right, then we should be able to create from first principle, have a very clear, unified understanding. I think we're sort of managed to do that, at least. So for the structure we discovered so far, provide rather unified explanation to what they have done. To be honest, maybe our earliest motive is trying to explain, to understand what we have done. But once we understood it, we realized that we can go much further, right? And realize even the current architectures, there's a lot of room for improvement. Not only we can dramatically simplify them. You can see in the past, after the create, in the past, last year and this year, there's a series of work from my group, right? Really just showcase people, right? You can actually, once you understand what is done with the principle, you can dramatically simplify. You can even throw away the MLP layer if you only care about the compression. You don't care about the final representation. Or you can make the attention head. Since we know what is optimizing, is optimizing the rate reduction object function, then we can find what is the equivalent variation form of that object function, which is much easier to optimize. We end up with we call it a toss, right? The computing the covariance, the self-tension step is only linear in the dimension, no longer quadratic, like the current tension is doing. Of course, if you look at the literature, there are other people have tried to identify linear complexity, such as Mamba, or I think there's RWVK or something. So empirically, but again, it's through trial and error. But this is so now we derive this in a purely mathematical way, because we just find the equivalent variational form of the same object function. They have the same global optimal, but it's just much easier to optimize. This is a trick we do all the time, right? All the tricks, see, in the 200 years plus years of developing better optimization algorithm, all those ideas can help us now to design better descent operators, or optimization architectures to improve the design of current architectures. Honestly, we have not really started that far, right? There's many acceleration techniques, preconditioning, conjugate gradient, which explore different landscape. Once we understand the landscape, the class of object function better, there's gazillions of ideas. We can further improve the efficiency. Honestly, we haven't started that far, right? I mean, that's actually got some of my students excited to pursue this, realizing how little we have done from an optimization perspective, how much room there might still be for improvement. Some of my students are quite excited. So you can see, even within the last couple of years, we already have 2 or 3 different generation of architectures that in the past, it's almost unthinkable, because the new generation always come from different group, right? It's like a random process. Whoever gets lucky, maybe discover something works. Try hard enough, get something to work.
It's a tantalizing idea, though, that through this principled optimization, there could be, a convergent evolution towards the optimum architecture.
Then the search will no longer be random, will be actually guided, right? There's still, just like back to your earlier suggestion, right? That this is becoming intelligent search, is guided search. We understand the structure of the problems now, and hence we can do science now. We are no longer just to do empirical, inductive search process.
Why do OpenAI, they're still using the transformer, even though there are now superior architectures out there? And we should talk about this token statistics transformer. So as you just said, it's a linear time complexity, which means in principle, this is something which is going to scale dramatically better than the kind of transformers we're using now. So why aren't we using it?
Well, there are attempts to try to scale this up. In fact, even you can think about many of course, when you try to scale, there are other factors that comes in, right? In terms of whether or not the scalability and so on. It's all related to all the design, indeed, we actually tried something else. For example, things are much more scalable. We also scaled up with all the resources we have. Sometimes, I don't know about company, right? We are very limited in resource. to verify even our those architecture scales, we can only do up to probably a few, couple hundred cars and so on. That's about it with our academic resources, and hopefully that will convince. But the one thing I think recently we did to simplify the current practice in Dino. Right, the Meta has to, which is the pre-trained, the state of art. Everybody talk about world model, visual world model, and that's sort of the best model. The Meta put a lot of effort, engineering effort, to pre-train the visual representation model, which is still the best. And they train on gazillions of images, and they were using contrastive learning. But it's a very remarkable engineering feat, and now people are using it, right? It turns out actually we found that the system can be dramatically simplified once we realize what the purpose, what they're actually really trying to do, right? We have a work called a SynDeno, simplified Deno, version 1, version 2. We simplify both versions. The architecture is dramatically so we get rid of dozens of hyperparameters. Don't have to do, and architecture become extremely 10 times simpler, and then the performance is better. We managed to scale up to probably a few hundred millions of scales. The apple-to-apple comparison were dramatically much easier to train, much efficient. Everything is explainable. I think that has a serious draw attention from the Meta team and also from the Google team. And it's currently I know there are serious effort that they're trying to scale the new architectures up.
Yes, we interviewed the Dino folks at the time, and we've spoken to people like Ishan Misra. There's a potential tangent there about they're using this kind of non-contrastive self-supervised learning, and also there's the whole unsupervised thing and how useful those representations are for downstream tasks. Maybe we could go there, but I should say that Kevin Murphy, I'm interviewing him soon, and I know that he reviewed your book very, very carefully, and he asked me to give you this question. He said, code reduction is great, but must be subject to prediction or reconstruction loss in data space. How would you go beyond token prediction, which seems especially weird for images? So that's what Kevin asked me to ask you.
So this is actually a great question, right? So in a re-reduction, remember the lossiness is actually coded through the epsilon ball. We're actually try to capture the samples, how they connect with one another. Right now, if we just minimizing the coding representation through this lossy coding, and the error is kind of controlled by the epsilon, but not enforced, right? So we respect the epsilon through this lossy coding process. Now, to truly ensure, remember, everything could go wrong. And it also depends on the number of samples you have. Maybe the epsilon you choose is wrong because the data does not have that density. So you not be able to percolate. Hence, the repetition learned can be very, very funky. So now, in order to ensure that your learned repetition, distribution you learn internally actually authentically reflect the original distribution up to a certain precision, you have to decode, right? There is a constant encoding, decoding. Actually, our brain do that all the time, predictive coding and so on and so forth. And hence, that encoding, decoding, and to verify if there's error remained in your prediction, in your reconstruction, matters a lot. Owning that, now the question is, if we don't have do we necessarily, back to our earlier discussion, right? Do we really need to measure that error in the data space, in the original token space? If we have that option, so be it. Do that, right? Make the engineering simpler, but if we really want to have a system just like a human, to self-learn, just go out to observe, right? With 2 eyes or with some sensors, then we have to come up with a way to make sure that our sensing process is accurate enough so that we can do everything internally. We can predict, go back, rapid back, and observe, compare what we predicted and what we observed through same sensing channel. We compare that locally. In theory, actually prove, at least under idealistic cases, this is possible. We can minimize the error. Once we correct the error, hence the internal representation will, the error in the token original data space will diminish. but under technical condition. Under general condition, we still don't know. We actually have a paper prove that when your data distribution is a mixture of subspaces, you can rigorously prove that's possible. And if the dimension of the subspace is low enough compared to the capacity of the perception process. Now, for general distribution, we believe this is true. This is actually how we'll be able to learn all the low-dimensional dynamics structure in the natural data, in the motion, in the predicted world. So I think this is something in the future we can deduct. But end-to-end works if you have the option to do so, or if you don't have that option, you have to figure out how to do this autonomously. Under what condition you can do this autonomously, and it allows you to do autonomously to reduce the error to almost zero.
We spoke about Dino, but another example would be VIT. We interviewed Lucas Bayer in Switzerland earlier this year, so he invented VIT. And if I understand correctly, Crate is now very, very close to VIT, but it's so much more principled, it's explainable, and so on. How close are we to knocking VIT off the leaderboard, if you like?
In fact, I think in many of the comparison, we're already very close. If you compare, it's hard to compare apple to apple, but in terms of if you use similar the parameters, we're very much on par. And also, by the way, we never really quite put much engineer effort into it. We just want to verify the concept. Indeed, one thing come out of the Crate is that what we found is not only the architecture design is principled, but then once we did the training, right, the internal structure learned are both semantically, statistically, and geometrically very meaningful. Indeed, each head actually does learns similar structures, all gets basically each channel, each head truly become an expert of certain type of visual patterns. For example, legs of animals, ears of animals, faces of animals. So we see that very clearly with crates, but we don't observe that in the VIT. Of course, you can see VIT may learn. This is actually the interesting thing, right? Early days, people, I'm sure, large models, if they have redundancy, they definitely learn things internally. But it's very hard to say which part of that network learn the correct channels, learn the correct operators, because it is embedded in a more some redundant structure, right? So early days, people call this lottery, lucky lottery or lottery ticket, right? It's somewhere in there, right? Then people try to distill. That justify you should distill. You should actually be able to compress. Even people do this LoRa thing, all the post-processing, right? Justify that is necessary. And some people you find after the post-processing, not only the network becomes smaller, the performance gets better, right? And so on and so forth. Now, probably we don't have to do that. At least, the architecture does what it's designed to do, right? And we can actually at least explain what each component is doing something statistically, geometrically very meaningful. And there are also results if there's enough data, if your optimization is done, training is successful, those structure pops up naturally. The structure would do what they're designed to do.
Yeah. And final question, many ML engineers and researchers watch the show. Given everything we've spoken about, how can they find out more about your work and how can they get started building these kind of architectures?
I think most of our architecture are open sourced on GitHub, including Crate, early ReduNet. ReduNet may not be as conceptual, but not very practical. Crate and also even Toast. All the codes are available. But by the way, they are sort of a kind of academic implement. We never be able to have the resource to scale them up. Most are scaled up to GPT-2 or ImageNet 21. That's sort of we can afford. Dino is the one we scale the most. We exhaust a lot of resource. A little bit higher than that, but still no comparison to all this industrial scale at all. But I do believe that Meta and Google are doing something about Dino, simplified Dino, and the codes are there. And also, of course, even for the methodology, of course, this is why we bite the bullet to wrote the book in the past 2 years. We believe that although there's a series of papers, but we believe that for people to get a big picture, the more systematic introduction, we put together the books. We open sourced it. And we will link all the data, all the code as well. we are also teaching the course. So we actually will have students practice most of the new architectures method. So all those codes will be made publicly available. And so I think that might be a good entrance if you want people who want to learn the methodology, understand the theoretical chain of evidence, and also even the empirical chain of evidence. And I think the book is attempt to do that. We are already start to organizing. We're not done yet, but we are already organizing. If you find out chapter 7, we're already doing that in chapter 7 to collect the theory seriously to all the real world data and the tasks, such as image classification, image segmentation, and the pre-training, and even language GPT-2 type scale language models as well. Yeah.
Professor Ma, it's been an absolute honor. Thank you so much for joining us today.
Yeah. Thank you very much. Yeah.